Today's lesson is about transformations of functions. I just want to bring you back to a slide we did maybe a couple weeks ago where we made a table for y equals x squared and for x minus 2 squared, and we then compared those graphs. Do you remember how with the tables we set up, we got the same y values, right? But for the x minus 2 graph, it took larger x values to produce the same y value. So that resulted in the graph shifting 2 units to the right because each x value had to be 2 units larger. That's just an explanation for why all those horizontal shifts and stretches and things are always going to seem opposite of the way they look in the, you know how it says minus 2, one might think left. Minus 2 is actually to the right, and that's why. Before we start talking about the other transformations, let's talk about the basic parent functions that you'll be able to graph really fast. That's the goal, is that if I say y equals x squared, you could throw down these 5 points no problem, because you can do 1 squared is 1, and you can do 2 squared is 4. Negative 1 squared is 1, negative 2 squared is 4. So those 5 points should just be really quick to throw on a graph. Same thing with all of these other parent functions. The square root function may be not as familiar, but the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So that's kind of an awkward set of points, but I was trying to choose nice x values that had square roots that we could just plot right on the crisscrosses. So square root of 1, 4, and 9 if you get a square root function. Then we're going to do the cubic and the cube root, which are also related. So I think we all know that 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. If you can remember that, that's going to be helpful. So then we'd also do negative 1 cubed is negative 1, negative 2 cubed is down at negative 8, and so we get this style of graph. Same thing for the cube root. But now the cube root is going to sort of switch the x and the y, right? So the cube root of 1 is 1, and the cube root of 8 is 2. So if I ever have you graph a cube root function, I'll be looking for these 5 points as the parent function. Cube root of negative 1 is negative 1, cube root of negative 8 is negative 2. And the last one I really want you to be familiar with is the absolute value function. Absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3, and the same outputs for the negative values. Absolute value of negative 1 is positive 1, positive 2, positive 3. So if you see an absolute value function, we'll start with those basic points. The two other parent functions are just the horizontal line and the sloped line. We aren't going to use those as much because we know so much about y equals mx plus b. Let's get into the shifts. The shifts are probably the easier part of this, just moving up, down, right, and left. Can you tell, though, sometimes the plus c is positioned here and sometimes the plus c is positioned next to the x value. If it's not right next to the x, that means it's going to be a vertical shift. So this is going to move the graph up c units. And this one, similarly, will move the graph down c units, where when it's inside the parentheses or it's grouped with the x value, that's going to be our left and right. So opposite, right? Our horizontals are opposite. So if you see a plus c, that's going to actually be left c units. Minus c would be right c units. So over here, if our parent function were that little square root function, what would happen if we threw a plus 4 under there? Can you see that that's grouped in with the x value? There aren't any parentheses in there, but they're sort of implied because that 4 is grouped with the x. So that would be a left or right. That would be a shift left 4 units. And then this plus one is not grouped in with the x. It's kind of an addition after the fact, so that one is an up 1. All right, let's do our graph. So when I get to a problem like this, I'm going to first think, okay, what is my parent function? It's the y equals the square root of x. So I'm going to go in there and I'm going to put on my key points. Square root of 1 is 1, square root of 4 is 2. If I had a 9 on this graph, I might put one more point. But these are the parent function. I'm not going to connect those because that's not my final answer anyway. But we just talked about how this plus 4 is going to move left 4, and the plus 1 is going to move up 1. So each of those points, I'm going to go left 4 and up 1. Left 4 and up 1. Left 4 and up 1. And then they're going to connect and look just like the shape of the parent function, only this one is shifted over. So that's just like a really quick way for you to make a graph of this function without having to make a dumb table of values or something. I remember I was in college, I was taking Calculus 1, and my teaching assistant would get up there and she'd just graph these functions off the top of her head, and I was always so amazed. I don't know if they didn't teach me this stuff in the 90s, but I think you're gonna wow everybody by being able to sketch just a quick graph of each of these functions just in your head. No graphing calculator needed. Reflections happen when we have a negative involved. If the negative is out in front of the graph, it's a vertical reflection. A negative grouped in with the x value. The x-axis is horizontal, so that's going to be a horizontal reflection. A couple of examples. If we started with a cube root function, which kind of is shaped like that, this one would get it reflected how? Since it's grouped with the x, that's a horizontal reflection. And then we have our little absolute value parent function. This one would be reflected how? That negative being out in front of the function is a vertical reflection. So flip it upside down. All right, let's do this. So we're going to start with just our regular cube root function here. And we have to know some key points to put on there. Oh, here's a flaw of my graph. I wish it went out to 8, right? Because 8, 2 would be one of my key points. Negative 8, negative 2 being one of my key points. So that's sort of that shape I was talking about earlier. So that's our cube root. And since that negative is a horizontal reflection, that just means we're going to flip everything that was on the right side of the axis goes to the left. Everything that was on the left side goes to the right. Just imagine everything flipping over the axis. So this point right here winds up over here. And this point right here winds up over here. Everything just flips horizontally. Positive x's become negative x's become positive x's. And that's the picture. One more reflection one, so we're going to graph just a regular old y equals absolute value of x, which is just one of those little v functions. This one is going to be vertically reflected, so we're going to flip the y values. It's going to look upside down. So something that used to be up at positive 3, now at negative 3. And that's a vertical reflection. Stretches and shrinks might just be a little more challenging for our graphing, but here's the idea. You're going to get a stretch or a shrink anytime you have something multiplied. So these are the vertical ones, so they're always going to be out in front of the function, not with the x. If the c is greater than 1, if it's 2 or 3 or 4, that means the y values are going to be doubled or tripled or quadrupled. So that's going to be a vertical stretch by a factor of whatever the number is. So I just say a vertical stretch by, it'll be c. And then if we have a number like half or a third, it's just going to shrink it down vertically by a half or by a third, each y value. It's called a vertical shrink. Now, that CU is probably going to look more like a fraction or a decimal less than 1. Here are some examples. So this first one is our regular old parabola parent function. If we stick a 2 out in front, that's going to take every y value times 2, and that's going to be a vertical stretch times 2, or by 2. Each y value would be multiplied by 2. Here we've got our cubic function, looking something like that. Since there's a 1/2 out in front, that's going to apply to the y values. The y values are each going to shrink down by half. So this is a vertical shrink by 1/2. Let's try one on a graph. This might be the challenging part. So first we're going to graph our parent function, the cube root of x. This is the one with the cube root of 8 is 2. Cube root of 1 is 1. -1, -1, -8, -2. Those are our parent function points. And hopefully you can see that that 3 out in the front is going to be a vertical stretch times 3, which, by the way, would mean our y values. Vertical means y value. So we're going to take each y value times 3. So for example, this guy right here, its y value is 1. 1 times 3 pops it up to here. This point over here, its y value is at 2. 2 times 3 stretches it up to there. This guy's at 0. 0 times 3 stays put. The y value now. The y value is -1 times 3 is -3. The y value here, -2 times 3 is -6. Connect those dots for our final answer. And that's a vertically stretched out cubic function. Horizontal. You know what's happening here. Horizontal is always opposite of how it seems. So if you're seeing a number like 2 or 3 or 4 grouped with that x, that's going to be a horizontal because it's grouped with the x. But in this case, since it's greater than 1, opposite of how it feels, this one's going to shrink. And it's going to shrink by a fraction of 1/c. You'll see that in the examples. Similarly, this one's going to be a stretch, even though you're going to see a 1/2 sitting there and think, well, that's good. No, it's a stretch by 1/1/2. Let's look at some examples. Here I've got my basic absolute value function. This guy's grouped in with the x, which tells me it's horizontal. A 2 is going to tell me it's a shrink. By how much? By 1/2. Horizontal shrink by 1/2. Next, we've got like a little parabola. And this is going to be a horizontal because it's grouped with the x. Horizontal, it's a 1/3, so it's a stretch. And 1 divided by 1/3 is 3. It's just the reciprocal, basically. So this would be a horizontal stretch by 3. Well, let's do it. So let's go with our parent function. We're going to graph a y equals x cubed for this guy. Hopefully you're starting to know where to put those points. 2 cubed is up at 8. -2 cubed is down at -8. And this 2/5, a horizontal. 2/5 makes me think shrink, but it's going to be stretch. By how much? By 5/2, which basically means I'm going to take each of my x values times 5/2 times 2.5. Here we go. So what would this point, so the x value, horizontal, 1 times 2.5, stretch out to here. 2 times 2.5, stretch out to 5. 0 times 2.5 stays put. -1, remember we're looking at the x values. -1 times 2.5 is -2.5. This guy is back at -2 times 2.5 would be negative 5. I want only the final answer to be connected, so it's really clear which one is your final graph. Doesn't that look like it got stretched out horizontally? That's perfect. Now there's an order of operations. Once we start combining and doing more than one reflection, it's based on PEMDAS. Any of those negatives out in front, which are like multiplication and anything that's multiplied, those are all gonna have to come first. And then we go to our shifts, which is the adding and subtracting pieces. So that's important that you do those in that order. So let's try this one. First, identifying the parent function, which would be just the absolute value function. I'd get those dots on there. And then we want to do the multiplying stuff first. So the multiplying stuff is out in front. Did you know that's actually two different, it looks like just a negative half, but that's actually two different transformations. The negative is a reflection, and the 1/2 is something else. Since that negative is out in front, that's more of a y value reflection. It's a vertical reflection. Also, that 1/2 out in front, it's a y value, and since it's multiplied times, that means stretch or shrink. So vertical, because it's not right next to the x, and this one would be a shrink by half. Let's just do our other transformation. We'll graph separately. This one is grouped in with the x, so I'm thinking horizontal, yeah? And since it's plus, minus sort of look, it's a shift. Would that be horizontal left or horizontal right? And the +3 is actually going to move us left 3. All right. But order of operations tells us that we have to do the multiplying and dividing first, the stretching and the shrinking first. So let's reflect and shrink by half. I don't know, should we try to do both of those at the same time? If we took this point right here and reflected it and then shrunk it by half, it would shrink up to -1. +1 times -1/2 would flip it over and then shrink it up. So I'm just taking my y values times -1/2. The y value here is +1 times -1/2. +2 times -1/2. You can see that it's a flipped upside down V, and it's a little squattier, a little vertically shrunk. And finally, we are going to move each of those points left 3. Left 3, left 3, left 3. And there's my graph. Sometimes it's not even possible to type these into your calculator, so if you've been planning on just getting away with that, not gonna happen. You're gonna have to be able to take just some funky piecewise function and do transformations to it. First, can you identify the 3 transformations going on here? Nothing is really grouped in with the x, so I think these are all vertical. We've got a vertical negative, so a vertical reflection. We've got a +2, so a vertical stretch times 2. And then the +1 is a vertical up or down, a vertical shift up by 1. And according to order of operations, we've got to do these guys first. So we're going to reflect and multiply by 2 for each y value. I might just start with the corners. Like this one right here is currently up at 2. And if I flip it and stretch it by 2, it's going to go down to -2, but then times 2, it'll wind up at -4. You could just take that +2 times -2. This one's at 0 for its y value. 0 times -2 stays put. Just doing those vertices. This one's up at y equals 3. 3 times -2 is going to flip it and stretch it down to here. And then we've got this guy right here that started at -2 times another -2. We'll flip it and stretch it up to 4. All right, can you sort of see what's going on? So we've got, I might just draw this in dotted so I don't lose track of how this is supposed to be shaped. Does that look like it got flipped and stretched? And now we just need to move each of those up by 1. So we'll do the up 1. And then connect those dots for our final answer. This last one's kind of a challenge. So f of x is going to be our original graph. And somehow that black graph transformed into that green graph. Well, I broke it down into 3 steps for you. The first step is it switched over to these sort of orange dots. Can you see how these 3 dots might have switched over to those other 3 orange dots? It should look like there's sort of a reflection going on there. Can you see it? Each of those dots got reflected horizontally. So that first one was a horizontal reflection. And we're going to look at how we got from the orange dot to the blue dot. So this one went to here, this one went to here, this one went to here. They kind of moved in, right? They kind of shrunk horizontally, is what I'm thinking, a horizontal shrink. By how much? I think they went halfway in, didn't they? If it was out at 5, now it's at 2.5. So a horizontal shrink of half. Okay, and then how did we get from blue dots to green dots, the final answer? So this one wound up here, this one wound up here, this one here. It looks like a shift down, yeah? Vertical shift down. How much was that? From 6 down by 6. Yeah? Okay. So here's the fun part. We have to put those 3 transformations into a final function. So we had our f of x. We actually had a couple of horizontal things going on, right? So those would go in the parentheses next to our x. And the shift down would go outside the parentheses. Okay, so I actually got this one already. So now I need inside the parentheses a reflection. So I'll need a negative there. And then a horizontal shrink by half. Remember, it's horizontal, so it's messed up. So that's actually going to look like the reciprocal in there. That 2 in there would cause a horizontal shrink by half. And that would be your answer. Like, that's what they're looking for. That's the equation that represents g of x in terms of that f of x.